All right, let's dive in. Today, we're going to crack open a really cool digital mystery. How does a machine actually learn to predict the future? We're going to explore this one elegant piece of math that allows technology to calculate the probability of, well, pretty much anything.
Okay, think about this for a second. You see this every single day. Your email filter pops up and says, with all this confidence, hey, there's a 93.2% chance this is spam. It's not 100, it's not 0, it's this super specific number. But where does that number even come from? How can a machine be so sure about something it's never seen before? And here's the real head scratcher. Probabilities have a really strict rule. They must live between 0 and 1. They can't be -1, they can't be 1.5. So how on earth do you build a machine that plays by that rule every single time? And that is the core problem we are going to unpack right now. And this brings us to what I like to call the 0 to 1 problem. It's this fundamental clash between how simple mathematical models work and the very rigid world of probability. So check this out. Here's the clash in action. On one side, you've got your basic linear models. Their calculations can spit out any number you can think of. 1,000,000, -5,000, you name it, it's all fair game. But then, on the other side, you have probabilities, which are stuck in that tiny little box between 0 and 1. You see the problem here? It's a huge mismatch. So that's the big question, right? How do you take a system that can produce basically infinite results and mathematically force its output into that super specific 0 to 1 range? And you can't just, chop off the numbers or something. You need an elegant way to map everything. Well, the answer, the hero of our story today, is this beautiful and, surprisingly simple mathematical tool. So let's meet the sigmoid function. So, the sigmoid function, it's famous for this really distinct S-shape, but its real superpower is its incredible ability to take any number you throw at it, doesn't matter how big, doesn't matter how small, and translate it perfectly into a value between 0 and 1. It's the exact mathematical bridge we've been looking for. Okay, and this chart, this is where you can really see the magic happen. Look at the input values along the bottom. See how when the input is a big negative number, the probability is super low. It's getting really close to 0. And right in the middle, at an input of 0, boom, exactly 0.5. And as the input gets positive, the output shoots up, getting closer and closer to 1. It just perfectly maps everything into our 0 to 1 range. Let's put some real numbers to this. If you feed the function a big negative number, like -7, it spits out 0.001, a teeny tiny probability. You feed it a 0, what do you get? Exactly 0.5, a perfect 50-50 shot. And if you give it a positive 7, you get back 0.999. That's a near certainty. It just gently squishes the entire infinite number line into our nice, neat probability range. So if there's one thing to take away, it's this. The best way to think about this thing is as the ultimate probability squeezer. It takes in all those raw, wild scores and just squeezes them into clean, usable probabilities. Okay, so how do machines actually use this probability squeezer? Well, it's a key part of a process called logistic regression. And honestly, it's a surprisingly simple two-step dance. No, really, it's incredibly straightforward. First, you've got a standard linear model that just does its thing. It takes all the features, like, say, the words in an email, and it calculates a raw score. We call this score z, or the log odds, and it can be any number. And then, for step 2, you just take that raw z-score and feed it right into our sigmoid function. That's it. It neatly spits out our final probability. And hey, just to be clear, that term log odds, I know it sounds a little intimidating, but it's really just the name for that raw middle score. It's what the model is thinking before it gets squeezed into a percentage that you and I can actually understand. All right, theory is great and all, but let's actually see this thing work. We're going to walk through a super quick example to put all the pieces together. Okay, so let's set the scene. Here are all the parts of a simple model we're going to use. We've got a bias, which is kind of like a starting point. We have a few weights, which tell the model how important each piece of input is. And then we have our inputs themselves, the actual data. All right, step 1. We need to calculate that raw score, z. Take a look at the numbers. What do you think z is going to be? And the answer is 1. Let's just quickly break that down. So we start with our bias, that's 1. Then we've got weight 1, which is 2, times its input, 0, so that's 0. Then weight 2, that's -1, times input, 10, that gives us -10. And finally, weight 3, which is 5, times its input, 2, that's +10. So you've got 1 plus 0 minus 10 plus 10. It all shakes out to just 1.
Awesome, we've got our z's. So now, for the final step, the grand finale. We take that score of z equals 1 and we feed it into our probability squeezer, the sigmoid function. What's the final probability going to be?
And the result is 0.731. And there you have it, the whole process start to finish. And if you remember that table from a minute ago, an input of 1 gives an output of exactly 0.731. Our two-step process worked perfectly. For this specific set of inputs, the model predicts a 73.1% probability. And that really is the big takeaway here. This incredibly simple idea, taking a straight line of calculation and just bending it with an S-curve, is actually the foundation for literally millions of yes or no decisions that power the technology we use every single day, from filtering spam to even helping with medical diagnoses. And it kind of leaves you with this fascinating question to think about. If this one simple, elegant curve is so powerful for these yes or no choices, what other kinds of shapes are out there right now teaching machines to do even more amazing things, like understanding language or seeing images, or maybe, just maybe, to think in ways we're only just starting to understand? Thanks for joining me.